Okay, hello, sorry. Hope everyone's doing okay. All right, let me share my screen. Thanks for coming. Sorry that I didn't post sooner. I thought I did. I could have sworn last night I was on my phone on Canvas at like 9 o'clock posting to all you guys. And I didn't. But okay, we got 30 people in here. So that's awesome. Um, I hate doing Zoom classes. I think this is always better in person. So what I'm going to do today, by the way, if you have my just like in class, please unmute and ask questions. You don't have to raise your hand or anything. I want to talk about something that I think is important, but never anything that I could test. And I think it's a good reason for Zoom to do this, because you don't get everything when we're remote. But you can always learn something. So we're going to learn something today. We're going to learn something today that you may not use, more, more for your intellectual stimulation. But I think it'll help. It'll help place. Actually, I think it'll help place chemistry in context, at least from my perspective. And I think that's kind of the goal of this lecture is to place chemistry in a greater context, physical chemistry in a greater context. Let's say chemistry as a whole in a greater context in the universe, from a physical perspective. All right, so let me share my screen. So what I want to talk about today is to just give you a taste. It's obviously something you can take multiple classes on, upper levels and even undergrad, as a physicist. But is the idea of the standard model, right? Which is the fundamental theory of physics, whatever you want to call it, where chemistry, of course, plays a huge role, right? And I want to talk about where chemistry falls into uh, the greater physical universe, where it's relevant in some sense. We can in some sense define the universe on a set of axes, not necessarily X, Y, and Z, but other axes that can teach us something about what kinds of things are going on at those points. And we'll see that in particular has to do with mass and distance. And so when we look at what's going on in the universe as a function of mass and distance, things tend to organize very, very nicely. And we can find exactly where chemistry is and how unbelievably limited chemistry is, and what we observe as what seems to be very complex, is really only a very small part of the universe in the mass and distance scale. So I want to understand just very, very basically, what does it look like? What does the mass and distance scale look like? And how does chemistry fit into it? How does some of the particles, like, electrons, we've been talking about electrons and atoms, where do they fall into place? What are they made up of? And how do they kind of fit into the bigger picture? So that's the standard model. And the standard model is a theory of two things that are interrelated, which are particles, electrons, as we'll see, protons and neutrons, and things like that, and forces. And we'll see that forces and particles are associated with each other. They're interrelated, in a very unique way. Trying to get rid of my meeting. And I want to talk about these two ideas. And I think it's best to start with forces, because I think we have a better appreciation for that. And then we can talk about particles and how they're associated with forces. And so there are four forces, what we call four fundamental forces in the universe. And what we're gonna identify, of course, is with a force is that there's something acting, applying that force, something that carries that force, and then there's a target for that force. Well, what does it act on, and who is applying the force, right? So that we have, in some sense, a messenger that we have to consider for the force, and we also have to consider, the target, the object that it's being acted on. So say the how do I want to say it? The type of work that's being applied. So the messenger and the application, right? Who's applying it and how is it being applied? And so we have to think about forces in those two ways. It's not just, as we'll see, not just, for instance, gravity, but what is a applying the force of gravity onto something else, and so on. And and of course, the one that we spend the most time talking about in as students, and when we go to school, we'll kind of we'll start with the first one. Sorry. The first force is, as we know, is that we understand most intuitively, of course, is gravity. Right. It's not entirely obvious how, when you observe gravity, when you drop something, how is it being applied, and what is applying it? Because in some sense, when you drop a ball, it feels like the ball is coming to the ground, and of course, then your physics teacher tells you that it's actually. You can also argue that the ball and the earth are coming together, right? That the earth is moving, and you've let the ball go, and the earth has now collided with the ball, right? There's multiple ways to kind of interpret a gravitational force, and so it's not really entirely clear how this applies here. Though we'll see in the other forces, it's much more clear what the messenger is and how it's being applied, right? But in some sense, we get the idea that gravity acts universally on everything of a mass. Which I want to call a very specific word, and I know it sounds a bit trite, but matter, right? It acts on all matter. It acts on bowling balls, and it also acts on electrons. Though we have some intuitive sense that it doesn't really matter that much for atoms, right? We don't think about the gravitational attraction between an atom and the ground. All right, we'll have to think about that idea. We'll come back to it. Right, and so we understand gravity as a function of mass, right? It's something that mass acts on another mass, right? We can always say that the force of gravity, right? This is what you learn in physics, is some big G constant times the mass m1 m2 over r squared, right? Right. It's like two masses acting on each other at some distance, being coupled by some gravitational constant, right? So it's like a mass acting on a mass, but it becomes more strange when you take gravity and you start to think about it from Einstein's point of view, right? This is Newton, right? We're talking 1700s here. Einstein comes along, right? And I don't have to go into the details of Einstein. I think the thing we learn about Einstein in elementary school, which is that energy is approximately equal to mc squared. By the way, it's only equal to mc squared for something that has no, like a photon, for light. If it's moving at the speed of light, it's equal when something's moving at the speed of light. But we'll say it's moving close to the speed of light. We can relate energy and mass together, right? Energy and mass in some sense are the same thing, because this is a constant. Right? So the speed of light gives you a conversion between mass and energy, right? So gravity in some sense is also at high energy, at high speeds, at relativistic, is also a theory of energy as well, right? So what we can also say is that this is also a theory of energy, right? But is that true? What about energy? We think of energy kind of in this sense of something like a bowling ball, with having some kinetic energy, some force when it impacts something, right? So momentum, I think, is the important question, right? And so it's easy to think about matter from this, but what about energy that doesn't have that kind of momentum? Well, the thing we've learned is that even the massless, which is photons, light even has energy. We showed that the momentum. Remember, even like quantum mechanics says that the momentum, even of something, so the magnitude of it, even of something that doesn't have mass, is h bar k, which is equal to h over lambda, right? That's what de Broglie told us, right? So even light, right? Even that, what that would mean is that gravity does affect light as well, right? Something that's massless. And it does, right? Light bends around space. Let me see if I can find a picture of it. We can show that gravity affects light directly because you can observe it in space when you have. Here's a really, it's called gravitational lensing. Let me show this picture of this. When you have something very massive blocking, impeding your path, say like you're looking at something far away, and there's something in between that object and you, and what you have is when it's sufficiently large enough, what you observe is this lensing effect. Right? So there's this massive star in the middle. This is close by. And way back here behind it, I don't know even how to draw this, right? You can imagine way back here at some distance is a little star that you're looking at, right? And it's propagating photons towards you. And this thing in front of you is so massive that it causes the light to bend around it, right? Which causes this lensing effect. Right? This is a three-dimensional effect. So you get this lensing effect, right? Where it looks, the thing that's way behind it looks way brighter. I mean, this ring looks quite bright, but it's not. It's just a small point behind it where the mass in front of it is large enough that it bends space and causes the light to go around it, causing a kind of a focal effect. It acts as like a lens, and so you get this lens like almost teardrop type shape from it from the lensing, right? So gravity affects light as well, right? We interpret that as that space and time is bending, right? That it's a curved surface that light is traveling, and we look straight in line, so it looks bent. But that also means that gravity affects light as well because matter and energy are the same thing. Okay, so gravity is very interesting. But the thing about gravity is that it's extremely weak. All right, I want to contextualize how weak it is soon. Right, we'll just hold on to gravity. Right, we'll just in general we'll just ignore gravity because it's so damn weak. Right, it only matters in massive, scales. We're talking about things that are billions of light years here apart. The thing that is lensing here is very, very, very far away. I don't know what I think the yellow thing might be already 5 billion light years away, and the thing behind it is even further away. This is a very early picture of the very early universe, regardless. So I think more interestingly is to think, right, we think gravity is the thing that dominates all of our physics until you get to small things, right? And then we start to see a new force appear, one that we've been already thinking about a lot, right? Which is the electromagnetic force. There's the electromagnetic force as well. And the electromagnetic force has a very, very clear way in which it interacts, has a very specific rules, and it also has a force carrier, as you find out. Right. And so what you find is, of course, that the carrier, what you have is that, of course, it acts on electromagnetic force acts on charges, right? Electrical charges. And there's one of the things that was discovered in the 2000s is that the thing that carries that force, the way that force is being what's acting, providing that action of force and attraction or repulsion between two electrons, the carrier or the force messenger, it's the photon, light. Right. And one of the things that you learn in physics is that if you have two electrons, and they collide with each other, you scatter them. And so they repel each other, right? So you have one going this way and one going this way, like a scattering process. And you ask the question, of course, they don't touch. There's no physical contact. In fact, the scattering length depends on their energy. Higher the energy, the further away they scatter. And you ask the question, when you calculate the angle at which they scatter. You ask the question, what is this angle here? Which is a function of the energy of the electron, like the energy of the electron. You find out that the only way to calculate this correctly, right, only accurate theory of theta of the energy of the electron requires that a photon be exchanged between the electrons. So what happens is at the deflection only can occur if a massless object, a photon, which is just some light particle, is exchanged between the particle between them. Right? And you can predict roughly what that effect is, where you make the assumption that this force is being exchanged with the release of a photon, which of course it has no mass and no charge. Okay, no mass and no charge, a neutral particle or neutral wave, if you will. It's got no charge. The prediction is good to 15 significant digits. Right? It's one of the best approximations we can make. 15 significant digits. So one photon is exchanged per scattering event between two electrons. You get an accuracy of theta to 13 or 15 significant digits. I might be exaggerating a little bit, but it's one of the most best predictions you can make. All right, so it's incredibly accurate. All right, so the photon acts as the object that interacts charges. And that should make a lot of sense, because if you think about the way that light is emitted and absorbed in chemistry, right? Things with electrons are emitting light, and things that have electrons are absorbing it. Right? We see light as in its intermediate state between emission and absorption, between two electromagnetic objects. Sometimes it exists for a long period of time before it gets reabsorbed by something. Sometimes it reflects and stuff. But that can also happen very intermittently as well. And something can be created and then destroyed in a short amount of time. All right, this is a really good prediction it turned out. All right, so that's a really interesting thing. So the question, of course, is now, right? So now you have charged particles, and you also have a force carrier, which is light. The important thing about the force carrier is that it's neutral. And in this case, it's massless. All right, we'll come back to charged particles in a second. All right, there's another interaction that we see called the weak force. Okay. And the weak force we only see in very certain situations, right? But we typically see this affecting nuclear decays and other high energy processes, right? But the most important thing, right, that we see in chemistry is that nuclear decays are heavily dependent on the weak force, in particular beta decay. Beta radiation is a strongly weak dependent thing. All right, and so you have to ask again the question, what does the weak force act on, and what does it, what carries it? You ask the question, what does it act on? Right, and it turns out that it acts on a very specific type of particle. It can be neutral or charged. but only particles with fractional spin, right? What do I mean by that? Well, that means like up-down deflecting atoms, right? So example, the silver atom, all right, let's not worry about the silver atom, the electron, right? It can either be in the Z plus or the Z minus states, right? Up or down deflecting, right? And we say that this is equal to something that has spin of 1/2. Right? And there's other types of spins as well. We'll look at ones that are, I'll come back to spin in a second. But it acts on a lot of different things, but it doesn't act on anything for instance, it doesn't act on the photon. Okay. We'll see. It does not act on the photon. And the carrier, there's 3 of them. And the interesting thing is they're so high energy, we hardly even care about them. They're called the W plus and minus and Z bosons. You've probably never heard of them. In fact, they were not discovered experimentally until the 1970s, I think. I think this was the 1970s. And the way you can think about this a little bit is that the weak force, what we say is it's weak because it's not a very strong force. And so in order to generate something that is modulated or modified by a very weak force, you have to look for actually need to be at really high energy. Right? I know that seems contradictory, but the idea is that as things become more high energy and chaotic, if you will, right, as you pump more energy into it, the less likely events become more likely. Right? If we remember in thermodynamics, we talk about equilibrium, right? It's always about the most likely thing, right? So it's the low energy processes that occur first. And so you have to pump the energy really high to get the really rare stuff. So when you think about weak, you should think rare. And so that means that the particles that would modulate those things are really rare, which means they have to be high energy, which means they're large mass. And you have these correlations between energy and time and mass. I'll come back to that in a second, right? And so we don't often think about these things because they're very, very rare. They exist only for very, very small amounts of time. They're very high energy because they're associated with very rare events. All right, but it's a more general thing. It acts on electrons and so on, and we'll see that in a second. All right, and then there's one more force, and I think this is the one that's perhaps the most interesting, other than the electromagnetic. It's called the strong force. And this is the glue in some sense that keeps our nuclei together. Right? And the nuclei are held together by 2 forces. So let's think about this. We'll come back to that in a little second. The strong force, what we say is it acts on. Interestingly, the strong force also acts on something that acts like a charge, right? But it's not what's called, it's a different type of charge. What we say is that they have what's called color charge. Right? It's a new type of, if you think about charges as being plus or minus, okay? Right? That's how we know charge. Color is another type of charge that has 6 different objects instead of 2, right? There's 2 choices for charge, plus and minus. Of course, they could be +1, -1, but you know that those correspond to changes of 1 electron, right? Electron only gives 1 charge. So it's either plus or minus. Color, there's 3 different options. Right? So there's 6 charges, 6 colors, as we say. All right, there's red, there's green, and there's blue. And then there's the corresponding anti-colors, as they're called. So there's anti-red, there's anti-green, and what would this one be? Anti-blue. I don't know what anti-blue is. We'll do this instead. Like these are the anti-colors. All right, so you can kind of think as this as being positive and this negative if you want. right? And there's three of them instead of just one. All right, and objects that are made with color, okay, are called objects with color are called hadrons, and which are made up of colored particles, colored components called quarks. Which are also combinations of colors or which are all I'm sorry of which are combinations of colors with zero color charge. Right, so all the colors cancel out. I know that sounds kind of weird. How do you have colors that cancel out? All right, we'll think about that in a second. All right, and so the idea is these six colors are what are called the force carriers, and they're called gluons. There are six of them. There's a red gluon, anti-red gluon, green minus gluon. And so the force carriers are the gluons. Okay. And gluons come together to make quarks, right? And they have to come together to make the quark the color total zero. All right, we won't go through the math of it, but the way to think about the math a little bit is that if we think about the electron, if we think about charge as being on a plus minus axis, so that my browser, sorry, I got a lot of stuff running on my computer. When we draw charge like that, the way you can kind of think about the math for color is that there are a triangle of axes. Let me see if I can color it right. Purple. This R G B R minus B minus B minus would be anti. And this is color, right? And so you could say, okay, well, something that is electrically neutral, and you add up all the positive charges, let's say I got some positive charges. I also have some negative charges that cancel it out, right? I get a +3 here and a -3 here. The same thing has to be true for a color neutral object as well. You have them moving in different directions, and you have to basically everything has to add back to zero, right? So these are, and so things that are made up of gluons are called quarks, and there are six quarks. All right, we'll talk about the quarks. All right, and what we could say is that hadrons, which are things like protons and neutrons, those are the things we care about in chemistry, are made up of three quarks for a color neutral object, I should say, as color neutral objects. So there's another type of charge called color. And the combination of the quarks determines the type of particle you get. So protons are a certain combination, neutrons are a certain other combination, and so on and so forth with the gluons. Gluons always come in pairs as well, because for complicated reasons, they in some sense they act opposite the electromagnetic force. And the important thing about the strong force, and this is what keeps nuclei together, So the strong force has a huge quirk. It gets stronger the further colored objects are apart. Right? This is why we call it the strong force. Think about the electromagnetic force when you separate two objects, or the gravitational force, when you separate two objects that attract each other by double the distance, they are now 4 times as weak. Force is much weaker. Strong force is the opposite of that. Strong force gets stronger as things pull apart. Right? So if you look at the force, I'll just draw it for you, right? This is the force for the electromagnetic force as a function of distance, and this is the force for the strong force, right? So this is between two charged particles, and this is two colored particles. Right? The electromagnetic force becomes negative like this, right? It becomes, remember, it's attractive. If it's a repulsive effect, it becomes weaker, right? So this is plus minus. Oh, sorry, that's not plus minus. This is between two pluses, and this is between plus minus. And the strong force between two objects goes like this. So what that means is that as you pull two colored objects apart, they pull each other back more and more and more, hence gluons. They're glued together. And the glue gets stickier and stickier and stickier as you pull them apart. Right? So that keeps protons and neutrons together. Right? That's the important thing about the strong force, is that it's opposite. It gets stronger the harder you pull on it. Right? So this keeps our nuclei together, and that's the important thing, right? Because protons and neutrons are neutral particles. They have no electromagnetic interaction between them. So how the hell do you keep them together in a nucleus? You keep them together with the strong force. Right? So these are strong force bound. Strong force keeps the nuclei together. Okay, so those are the four forces. You then ask the question, what's the relative scale of the four forces? Right? I've just mentioned four forces, but how do they all kind of fit on the same categories, right? So let's just summarize really quickly. We'll look at the relative strength. Gravity, EM, weak, and strong. And the best way to think about this is to think about the electromagnetic force as being one. Okay, we'll do everything relative to EM. Okay, so this is the strength of the electromagnetic force. It turns out to be, if you want to do it on a proper scale, is 1 to the 119th or something like that, but just assume it's 1. The strong force is about 60 times the strength. The weak force is about 1,000 times or 10,000 times stronger. Actually, hold on. Let me say that 10 to the 7, about 1,000,000 times weaker. Sorry, it's 10 million times weaker. And gravity is 10 to the minus 36 times weaker. This is why we don't ever think about gravity in chemistry, because it's entirely irrelevant. So those are our forces. In fact, what I'm going to do is this. I'll make this a little smaller. So, okay. So let's talk about how matter is composed. And I'm running out of time, actually. Wait, hold on a second. It's 12:30. Oh, no, we got time. Okay, great. All right, so let's talk about how matter is composed, right? So we have four forces, one of which doesn't matter. right? We just ignore completely. And how do the three forces kind of interact? How does matter interact in such a way to give you particles, right? And the best way to think about particles, all right, is to remember at speeds near the rate of speed of light. So speeds near the speed of light, right? We can always write that the energy is equal to mass e squared, right? We always come back to this. This is super important. And the idea is that we shouldn't think about things so much as an object with mass anymore necessarily, but an object also with energy. These are interconnected with each other. Right? So what that means is that at speeds near c, excitations, energetic excitations of a system, right, which are like energy levels, right? You can think of those as masses, right? They have a mass. Right. So at high speeds, at high energy, it's not really reason. It's in some sense, it's not really all that useful to think about the energy levels of an object. Rather, you should think of the object as space, and then what you're doing is you're putting energy into the universe, the vacuum or whatever you want to call it, and you're creating objects of mass. And there's different types of objects of mass that you can create. Some mass has interacts electromagnetically with mass, and some don't, right? Like the photon, right? So there's different types of mass, some of which interact in the way that we understand mass. And then there's some things that, in some sense, we think of as pure energy, right? They don't have the same kind of mass that we do. And of course, what that means is that it's traveling at the speed of light. So objects that don't travel at the speed of light always have an inertial mass that we can feel. All right, so that's everything else. The electron, the photon, the electron, the proton, the neutron, they all have masses because they don't travel at the speed of light. And I know that's kind of a circular logic, but it just is a good way to kind of think about it. So let's think about how things are organized. And what I want to think about is that there are essential properties that everything shares. We've already talked about some of them. Right? One of them, of course, is the mass. One of them is the charge, right, which tells you whether it interacts with EM, right, the electromagnetic field. Right? Things with charge interact with electromagnetism. There's the color, right? That's the strong force. Right? And then the other thing that's important is what's called the spin, right? And we'll talk a lot about spin in this class. We have to talk about it when we talk about the atom. The atom is built on spin. Right? But I'll introduce an interesting concept about spin. Just a 2-minute introduction, right? It's an intrinsic angular momentum for an object. Right. And the way I like to think about spin is through the electron, right? We've already talked about spin, up deflecting and down deflecting. One way I like to think about the electron is, again, if you think about the electron as a wave, right? And it's got two components. It's got the longitudinal component, and it's got the transverse component. Right? This is an electron. The electromagnetic field of the electron also has a helicity to it, meaning it's spinning relative to the axis. So what I mean by that is that these waves are exchanging. So this wave goes here, this wave comes out of the plane, this wave goes into the plane, and so on and so forth, right? So it's got this helicity, right? So I can kind of draw it like this. Right? As it's propagating, it's rotating, and there's two different ways to rotate. Right? There's this way, Right, we'll call that the plus rotation. And then there's correspondingly an anti-rotation, where it could be rotating this way. Right? And we associate these with two different spins. Right? So we say that this is the plus 1/2 spin, and this is the minus 1/2 spin. So we say an electron has spin 1/2, and those are the two possible states. Right? They have like a helicity of the field. They have some circular motion along the path. Turns out this is a very kind of it's more complicated than this because you can have all sorts of different types of spins. Right? It's not just 1/2 and minus 1/2, but other types. So we'll have to think about this a little bit. But that's a good way to think about it. This is a good way to think about a spin 1/2 object. But spin can take any number that's fractional or integer, it turns out. Okay, so there's two types of objects, two types of spin objects. And we correlate them between what are called bosons and fermions. Right? And bosons have integer spin. All right, so they can be spin 1. Right? The photon is spin 1. They can also be spin 0, meaning they have no angular momentum ever. Right? There's only one object in the known universe that has this. There's two. There's two. The Higgs and Z bosons. Right? What that means is they have no spin. They just are like just flat waves, if you will, and so on and so forth. And fermions have half integer spin. Right? And the vast majority of things are 1/2. Right? Like the electron and the proton and the neutron. Okay. Bosons, fermions have one important distinction. And we can talk about the math of this later. It will become important when we talk about molecules. In fact, this distinction between bosons and fermions is one of the reasons why we have chemistry. Bosons do not. Bosons. So let me actually say this. So let me say what fermions can't do. I think that's more important. Fermions have a limitation that bosons do not. They follow a principle called Pauli, named after Wolfgang Pauli, Pauli exclusion principle. Which says that only one particle in a given state and position can exist simultaneously. So what this means is, right, you guys know this implicitly because you can only put two electrons in an orbital. Right? It's been a spin up, and a spin down. Two electrons in an orbital, and you start filling the electrons, right? The orbitals after that, right? 1s, 2s, right? The octet roll, all that junk. Right? That's because they follow this Pauli exclusion principle, meaning if you have a spin up electron in an orbital, it's the only one that can be there. You can't bring another one in. All right. The other one that has to come into that orbital has to be a different spin. Okay. So what that means is that if you have a wave function for some particle that's at some position x and some position, some energy state E sub n, in some spin, we'll say plus or minus, say plus 1/2. And you ask the question, how many can be in that state? It's one. You can only have one. Bosons don't have that property. Bosons can stack. right? If photons were fermions, you could only have one photon in your room at a time at a given energy and a given spin, right? So there would be only two photons in a given room, a given space of a given energy at one time. Of course, that's impossible. There's trillions upon trillions and trillions of photons streaming into this room right now. And the reason, and they're all roughly the same energy, right? There's a spectrum of them. White lights, that means there's lots of different colors, but there means there's billions of blue photons and billions of red photons. They're all the same energy. They're all moving exactly the same way, all identical, right? That's because photons are bosons, and you can stack them all up in the same state, and you've got no problem. Can't do that with electrons. You can only have one electron per state. So you kind of have this subdivision of matter, this fundamental subdivision of things that have integer spin and things that don't, and they follow completely different rules. And it turns out that their interactions in physics are extremely important. They fall, in some sense, they fall into two different classes. All right, so we have fermions here on the left. We're just going to kind of classify things together. Right? And we have bosons over here. Right? Completely different interactions. Right? Bosons, you can stack them. So they love to stack. And these hate to stack. Actually, I shouldn't even say they hate the stack. I mean, it's like stacking's not even possible for them. They don't even dislike it. There's not some force that pushes them away. It's impossible for them to stack. Completely different. And then you can think about how matter interact, how matter falls into them, into these categories. So so matter kind of separates itself into these two categories, fermion and bosons. It's matter. I'll start with the bosons because there's less of them. All right, and they're split into by their spins. So their spin equals 0. There's a category of spin equals 0. And there's a category of spin equals 1. Now, what is spin equals 1? Well, this means that there are 3 states of spin. So S can be either -1, 0, or +1. And the way to think about this is with light. We'll come back to that. Light has 3 polarizations. There's left circular, right circular, and linear. Right? If you've ever had circularly polarized sunglasses, you have an appreciation for this. Circularly polarized sunglasses block out polarized light, not and let linear light in, right, which blocks the UVs and so on and dims things a little bit. Right? There's different types of polarizations, so we call those spins. The math works. Polarization math works exactly the same way as spin does. Right? And there's only one spin 0 particle, the Higgs boson. Right? This is the God particle that you discovered in 2012, right, at the LHC. It's it turns out it's the thing that kind of ties everything together. Right? We won't worry about that. And then there are the spin 1 ones, and there's 3 kinds, right? 3 flavors, if you will. There's the photon. There's the W and Z bosons, right? These are the weak force. This is the electromagnetic force, right? Force carrier. And then the gluons, the strong force. So the force carriers are all bosons, and they all have what's called spin, right? They have some spin, meaning that there's different ways to polarize them, right? You can have left circularly polarized force, right circularly polarized force, and linearly polarized force, right? So light is the best way to think about this, right? So all the force carriers are bosons, and that should make sense, right? Because if you want to make a stronger force, you have to stack more force carrying objects together, and you better hope that they can all stack together, right? So all our force carriers are bosons, right? The fermions are a little more interesting. Fermions are matter in some sense. There are no massless fermions. They all have mass. They don't necessarily have size, but they all have mass. All right, we can actually split them into two categories. There are what are called the leptons. These are spin 1/2. They have integer charge, +1, -1, and so on, right? And no color. Okay. And there are three kinds. They're all very similar to each other. There's the electron, E minus. There's what's called the muon, U minus. So minus. And there's the tau. You can think of them as they all have the same properties, except they have different masses. The muon and the tau are very heavy. All right, I'll write the masses down in just a second. And the electron is very light. And you can kind of think of these as excited states of the electron. Close this up. These are kind of like excited electrons. Right? And remember, when you excite something that's moving near the speed of light, you're creating more mass, right? E equals mc squared. So these are excited state of electrons, and of course they decay into each other. So tau decays into muons, and muons decays into electrons, and electrons are the fundamental particle. They don't break down anymore. Right? So you can think of them as just excited states. Interestingly, and no one knows the answer to why this is, there is nothing beyond tau. No one's been able to find the fourth. There's an additional set of particles that also count in here that are neutral. So then we have spin 1/2 neutral particles. And these are called the neutrinos. They're small. And there are three of them. There's the electron neutrino, the muon neutrino, and the tau neutrino. Right? So they're named after their massive part, their friends. They're not their charged friends. Right? And they're very rarely seen, but there's tons of them. They're ubiquitous. But likely very, very small mass. Right? It's very hard to see them, but people can find them. And when you detect them, you can initiate. You basically find that it's the most common thing other than the photon in the universe. There are neutrinos streaming out of everything. Right? They just very rarely interact because they're very, very weak, very small mass. They don't interact with a lot of stuff because they're neutral. They don't have charge. So, so they only interact through the weak force. Okay. So they only interact with other things through the weak force. So you have to have neutrons and protons, and you have to have lots of atoms, huge detectors that can detect them and scatter them. And sometimes, you spend an entire year and you find 12 of them or something like that. All right. So they're very weak, but very, very common. So anytime there's nuclear decay, high energy processes out of the sun, they're constantly streaming. Right. Tons of them. Finally, there's what are called the quarks. Sorry, yeah, the baryons. Let me put here. right? And these are objects that are spin one half. Oh, sorry, let me call this. Sorry, let's not go to quarks yet. Let's go to, then we have the quarks. We're doing fundamental particles, I bet, which are spin one half, just like them, but they have fractional charge. I'll tell you what I mean by that in a second. And they have color. Right? And there are 6 different kinds. There's the up, the down, the charm, the strange, the top, and the bottom. Okay. And quarks are made up of gluons. They're made up of pairs of gluons, right? So these are made up of gluons, gluon combinations. So they're made up of color. And you can combine quarks. Quarks come in pairs. Quarks love to come together, all right, to make composite particles, which are called baryons. And we know 2 baryons in particular that are extremely important. The 2 lowest energy ones, they're the proton, which is, I think is, let me just double check. I think it's up, anti-up. Yep, it's up, up, down. So this is the up quark, the up 2 up quarks and a down quark. And then there's the neutron. And let me find the right combo of this too. Up, down, down. Okay. So, and of course, you can make all sorts of other baryons, tons of other ways to combine quarks. You can bring anti-quarks in, you can bring top, bottom, charms, strange, all of them can come in and make all these crazy little particles, right? So when you go look at, if you go look at like when there's press releases from the big particle accelerators, there used to be one in Stony Brook. They don't really do high energy physics anymore. No, that's not true. They do lead collisions, lead ion collisions. There's the one in Chicago called Tevatron, which they just decommissioned in the last 10 years. The Large Hadron Collider. You'll see that they always publish these things where they detect a new particle, some new exciting thing at high energy. Most of these correspond to either basically new combinations of quarks that they put together that are very unstable, that fall apart basically instantly. Other types of decay products, kinetics, energies, things like that. They measure the properties of these things. So baryons are an extremely important part of physics. In some sense, it's the physics that of the nucleus, right? The things that creates the nucleus, and it has its own chemistry of color, the color chemistry of it, right? And so a lot of people do high energy physicists study the color chemistry of the baryons. Very common thing for them to do, but not really all that relevant for chemistry. Okay, and so we can kind of just like zoom out for a minute and stop here for a sec and just kind of get an idea. So the things that are important that are important in energy and physics are important for us as well in chemistry, right? Charge is important, mass is important, spin is important. Right, we're going to also we've already seen spin in its own way. Of course, mass, of course, is always important. And charge is extraordinarily important, as we'll see when we get to the hydrogen atom. The hydrogen atom is built around the concept of charge, right? The stabilization of positive and negative, interaction of positive and negatives. And so these forces come from basically the source of them is unknown, right? It's not really clear. One of the unsolved problems in physics is what is the organizing principle of all of these. One of the things that you might think is about that you sense that there's some structure here is that we see these properties at very high energies and then at very low energies. and these properties seem self-organizing, right? If we go back to our picture here of the different types of particles, right? They're all connected by these specific properties, whether they have charge, they don't have charge, they have certain type of spin, right? Depending on determines their statistics, as we'll see. They have color, they don't have color, which is a different type of charge, or this three-dimensional charge, if you will. And that's all ultimately all that determines the differences between these things. Just like in chemistry, right? Chemistry, we have a periodic table that's largely just determined by how many protons you have, right? How many positive charges in the nucleus. Of course, the neutrons also matter as well. So there's just some organizing principles that we see. And we see it all the way down at low energy. And what I mean by low energy is the things that we observe at 0 Kelvin, and 300 Kelvin is not a lot of energy either. Room temperature is pretty low energy. And what I want to show you finally is to start thinking a little bit more about this idea. Is to think about how do we organize these things, right? And I want to go back to that original idea that Newton had, or that Einstein had, which is that mass and energy are correlated with each other. But another thing that Einstein also realized is that distance and energy are also correlated with each other as well. That you can relate distance or size as well to an energy scale. They're independent. Mass and length, of course, are independent properties. You can have something that's long and small and something that's short and fat and dense, right? You have a density. And so density is the independent parameter, and it can be two different independent parameters, mass and distance scale. And so if you can think about the universe and how it organizes it on that scale, what you find is that actually things tend to be quite organized very nicely. And this is a really beautiful plot that was published a couple years ago. And I want to spend a couple minutes on this plot because it places chemistry in a really important context. One of the things that we think about in PChem, let's just first talk about this and then find where PChem sits on this plot. So the mass, the scale, the plot, this plot is a two, there's lots of axes, but all these axes are just different units. Okay. And the important thing is that we're on this scale, on the y-axis, this is mass, and on the x-axis, this is distance or size. All right, I don't know how you want to think about it, but either one, be a diameter, if you will. Okay, so just remember that pi, and it's on log scale. Okay, so we're on a logarithmic scale. So you notice this scale, this goes many, many, many orders of magnitude in energy and mass, or sorry, mass and distance. And so what this does is basically looks at every object that we know in terms of its mass and its distance and puts it on this scale. And what you find is that it's very well organized. And the important thing is that there's two kind of limits to matter on this scale. All right, we'll talk a little bit more about this distance. So there's this line right here. I draw here, which he calls the Compton limit. And the Compton limit, which I've already written over here, is in some sense the wavelength of the photon, the energy of the photon that is equivalent to a mass of an object. Right? So you have some matter object, and you can relate that right through what do you call it? You can put it some energy and you can relate its momentum in some sense to the wavelength. So you ask the question, what is the equivalent wavelength for a particle at a given mass energy? And that's the Compton limit, right? But basically, after the Compton limit here, as it says quantum uncertainty, the wavelength of a particle is exactly the same as the equivalent photon. So in some sense, you can't tell them apart anymore. Matter is kind of broken down. It's just pure energy at that point. Right, so we call that the Compton limit. All right, so you can imagine this region is that space where the concept of space doesn't really, or like a size for something doesn't really matter anymore because it has the same amount of energy as the equivalent photon. And then there's this other side, this other one, the large limit, this y axis, which is black holes. If you have a mass, if you have density even higher than this, it collapses in on itself. Okay, so this gives us, in some sense, an energy size limit on both scales, the large mass limit, large distance limit, and the small distance high energy limit. Right, so this is quantum mechanics. Right, this is basically where wavelengths are so things are oscillating so fast, calling it matter is irrelevant. And up here, gravity doesn't let you do anything. Okay, so everything falls into this little region in between these two limits. And let's just look at, if you notice, most of this region in this section that I'm just going to finish drawing here is empty. There's not really a lot in there, and in fact, most of the stuff lies in certain regions. Right? You can see now as I lie along the Compton limit, right? All of my particles, quantum particles, the leptons and the baryon, not the leptons, but the fundamental particles are all there. The leptons and the bosons and stuff like that. There's the photon. Here's the electron. Here's the proton, the neutron, the bosons, and this is the top quark, right? So this is the section where high energy physics basically ceases to exist, right? The idea that matter is organized into distinct particles, it breaks down at this point. And then we can identify immediately where chemistry appears. Right? Chemistry appears right here. Right? Atoms are just this small region. And I'm gonna add fleas and humans and whales because they're chemical objects as well. They're biochemical objects, right? But this is basically chemistry. You can see once we get up to larger scales, we start to get to astronomy, right? And this is this is as the universe gets larger, and so on and so forth, right? But the important thing is that this is where matter is organized in 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 the universe, right? There's a strip of things that we appreciate, biological and chemical matter, that sits kind of in that green strand, and then there's the astronomical matter, which kind of sits way up here by itself, and the rest is nothing. No, there's just huge gaps in our matter in this distribution, which are filled with nothing other than energy. In fact, you may notice this color right here. This tells you what kind of energy dominates in that mass region in this pink area. This R just means radiation. So in these large spaces here that I'm drawing in yellow, right? The only things that really exist in this space are photons. If you go count by energy, it's just mostly photons. And you can see here that the vast majority of matter sits in this little band right here that I've drawn. I'm going to draw it in a different color. Draw it in red. Right? That band right there. That's the vast majority of the mass in the universe. Right? And so this M here is for matter. And then you ask the question, well, there's this whole space here. What's in there? Well, nothing. This is what's called dark energy, right? Which turns out to be the energy from the expansion of it. It's a long story, but basically this is nothing, right? There's a whole gap of mass that hasn't formed yet. Right? This is our mass is slowly pushing out this direction as things cool. And this is slowly going to push this way. But the important thing is that all of our physics fall into these very, very narrow strips of categories of space. These three right here, right? This is high energy physics that we've talked about. This is astronomy up here. Here's chemistry. And here's biology, right? On this scale, the universe is very, very sparse. And so this really puts chemistry into context. we've spent all our time down here, and of course we could spend all our time at the top of the mass. All things are very interesting here, but this is the important thing: is that chemistry is low mass. Actually, it's not even low mass; it's intermediate mass, low energy, and electromagnetic dominated. Chemistry is the theory of the electromagnetic interaction at low energy and at high mass. So we don't ever have to worry about the strong or the weak force so much in chemistry because we're not anywhere near the right size or mass, the mass or length scales to worry about that. Rather, we only have to worry about the strongest force that's available, which is the electromagnetic. So chemistry ultimately comes down to the interactions between electrons and protons. This is the most important part. The final thing that we need to consider, my final statement, is how do they interact with each other, electrons and protons? Right? They interact through the charge, but the important thing about them is they have a massive mass difference. And this is the thing that we're going to have to start exploring when we talk about molecules. If we take the mass of the electron and we take the mass of the proton, what we find is that they're about a 1 in 1,000th apart, about 1,000th of the size. And so the protons are really, really fat compared to the electrons. And what we're going to find is by taking that approximation to realize that the protons are so giant and that the electrons are just bouncing around them very, very rapidly. Their mass is smaller, but so therefore, on average, if they have the same energy, they're moving more quickly. You assume they have the same energy, same potential energy. They're going to be moving at roughly 100 times faster or something like that, 50 times faster. Then we can think about the protons basically being stationary in a molecule. Electrons are bouncing around them. And it turns out that that's a key assumption in chemistry and allows us to basically derive molecular structure from that idea. Right? Like the concept of having molecules having structure comes from the fact that protons are much heavier than electrons. All right, so that's what we're going to explore starting next week. We're going to start freezing protons and freezing atoms together and thinking about how electrons move around them. Right, that's going to allow us to talk about bonds. Then we're going to think about how electrons are captured within atoms. We'll talk about hydrogen, and then we'll start putting things together to putting atoms together with bonds to make molecules and thinking about how electrons are shared amongst atoms using bonds and molecules. And eventually we'll be able to build out a theory of chemistry and chemical structure coming just from the pure assumption that everything is controlled by electromagnetism. Okay, with just pluses and minus charges and the interactions of things that may or may not be neutral. Okay, so that's what I got for you today. Right on time. Thank you all. I'll post this online. We'll come back starting on Monday. We'll do we'll start talking about molecules and bonds. All right. Have a good one, everybody. Thank you.
Thank you.
Thank you. Have a good day.
Thank you.